going to introduce Anna, who's going to talk about area of asymmetry and galaxy clustering.
Hello everyone, my name is Anna Durkalec. I am, as of recently, assistant professor at the National Center for Nuclear Research, and I'm going to talk a little bit about a little, side project, a little bit, let's say it, because this is not what I'm doing recently since being very occupied with LSST. But this is a project that was, how to say, born out of frustration at some point, but we will see how it goes. So, halo asymmetry and galaxy clustering, as we all know, there is one of the biggest questions is how to marry the luminous part of the universe with the dark part of the luminous, with the dark part of the universe. So, you understand the relationship between galaxies and the underlying dark matter distribution. So there's a very many methods that we've had as of today even to solve this problem. However, one of the methods, a very historical method, is using the two-point correlation function, which is a very neat tool by usually just counting the pairs of galaxies and checking if the number of these pairs is above random, which usually is. Okay, this is your baseline. This is your correlation function that you're measuring, but you want to know something from this correlation function, so you need some model. This model that I'm going to focus today is called the halo occupation distribution modeling, which is used to determine, based on the two-point correlation function of endpoint correlation function events, to determine, what are the halo masses of galaxies that you just measured. For which you just measure the correlation function. So for those who are unfamiliar with HOD, this is just a summary with like a schematic and stuff. Basically, it depends on two basic assumptions. Galaxies are residing within the dark matter halos, and the number of galaxies within these halos is related to the mass of the halo. Simple as this, there is a number of parameters that it's describing this halo model. Classical form, the number of parameters vary from 3 to 5, but this is early 2010s, let's say. Since then, there's a lot of effort has been made to improve these models, to add something that's called assembly biases, little teeny tiny effects that may influence the halo relation, the halo mass relation with the galaxies, like velocities of galaxies, environmental biases, this kind of stuff. So you might have noticed one of these things. The problem with these models, these sophisticated models that we have right now, is that there are multi-parameters. So if you have a small sample, there are nice, but you can't do anything with them because you have a less number of measurement points than the number of parameters. So your modeling is not very well constrained. So this was the case for me when I had like very small sample of galaxies in woods, and I decided, okay, I can fit 30 parameters to my 8 points, but this is not going to do anything. But I can somehow check if I can, pinpoint one single effect that I might add and see what's going to happen with my correlation function, of modeling of my correlation function. So I was thinking a little bit about it, and I just kind of noticed one thing. So I made this schematic of how to explain the HOD. And there is one thing which some of you also might have noticed. This is like in this joke about the physicist who is solving a problem for a farmer who asked him how to solve the overcrowding of my cows on my field. And the physicist is saying, I can solve your problem, but if we assume that your cows are spherically symmetrical and in vacuum. So this can also apply to halos, the dark matter halos, in the classical models, which are very well, I'm not shaming the classical models here. I'm using them all the time. but we are sort of treating the dark matter halos as a spherical chaos in the universe in this case. So I was thinking, how can I single out this one simple problem about halo symmetry and see if it's going to change anything if I modify a model a little bit. But keep in mind, I still wanted to keep the model very simple. So I don't want to add like 10 additional parameters to describe the asymmetry. I want only one. So just to keep it simple. Okay. So this is just to justify this idea. In simulations, if you do and count all of the shapes of the halos, and let's divide this for the sake of simplicity. Again, let's divide the shapes of the halos as ellipsoidal shapes. So you have prolate halos, you have spherical halos, and you have oblate halos. But this is too much Latin, so you can say this is eggs, football, and pancakes. So if you just count the number of halos as masses of the galaxies who are residing in these halos, and this is just a description of the shape. So you can tell that it has a dependency on the mass of the galaxies that are residing within the halos. So the most massive halos are preferably occupying the prolate halos, which like egg-shaped like. So and this is changing with mass. So this is one of the dependencies here. Okay, so I said I wanted to add one parameter only, so I called it phi. There's a Greek alphabet, choose your favorite letter. And this parameter is going to take values between 0 and infinity, with the assumption that phi equal 1 equals to spherical symmetry of the halo. So I wanted to check how this parameter is. I just left it as a free parameter and just check what the value of this parameter is going to change, how this value is going to change when I fit it to the correlation function. So the base of the HOD, the classical base of the HOD stays the same. So we have 5 parameters. The 3 masses and alpha and sigma. But now we are just going to slightly modify NFW profile, which is taking this form. So since I assume that the galaxy halos have like prolate or spherical oblate shapes, this is going to be the description of the halo radius. If you do some, mathing, algebra, you can change it to this side, but still you're staying with the values of the axis of the ellipsoid. So you can just assume that this is going to be your parameter phi. So just combine them all together and see. So your phi is literally describing the deviation from the spherical symmetry. So if you just model it, just to run the model for this, if you notice here, the changes with phi are mostly for the one halo term, so whatever is happening within one halo between galaxies. So if this parameter is made in that way, so this is the correlation function, the projected correlation function, and this is the model. This is no observations yet or anything. So if you have phi 1 and you keep all of the other parameters the same, but change only phi, this is how your correlation function is going to change. Okay, so of course you have a new model, you want to test it. I used the to test it, I used Bolshoi simulations. So this is now, we populated the simulations with halo tool, with halos and then galaxies inside them. And nice thing about the simulations that you have all of the information. So if you do your blind fitting, then you can check if your fitting fits. If your fitting fits and if your fitting is retrieving the same results as you would get from the simulations. So I divided my sample into 3 different stellar mass samples, my galaxies into 3 different, measure the correlation function, which is these points, then made a fit, which is the solid line, and then I checked how it's going to change if I would just use the same halo parameters, the same 5 parameters, but that I got from this fit. But I assume that this is a spherical symmetry, so how this function would change. So as you can see, the changes between two models are not super big for low massive galaxies, but it's increasingly bigger for most massive galaxies. Since I have the simulations, I can check if my phi parameter is similar to the true results. So the points are the fitting point, the points I got from the fitting for different galaxy samples, and the line is true results and the standard deviation. So the same for the halo masses, if I am able to retrieve the halo mass as a function of the stellar mass of the galaxies. And this is again the same thing. Points are my fitting points, and the points that I got from the correlation function fitting, and these are the real values. Okay, but how is it going to work for the observations? So I asked one of the authors of the very famous paper from Zahavi et al. From 2011, they did they measured the correlation function in HOD modeling based on the SDSS data, and they gave me the results so I could compare to them. But first, I wanted to check how the phi is gonna change for their samples. So they had samples that are divided into the luminosity. So they measured the correlation function for different luminosity samples. And I repeated the measurement with my model, and I got the values of phi. As you can see, the asymmetry of the halo is quite drastically changing with the luminosity, with the increasing luminosity of galaxies. So the last slide is just to compare the parameters that I got. So again, the dashed lines are the results from the original paper from 2011 from Zahavi et al. They were using spherically symmetrical model. And the points that I have here is from my fitting with includes asymmetry. So as you can see, they are a little bit different. So we're measuring between 2 to 6% difference. So I'm going to just leave you with conclusion. If you are interested in more details about this project, it's in my paper from 2024. And I just want to say that this was a very simple project to just check one effect on galaxy clustering and how it can change or improve our measurements of halo masses. Thank you very much.
Thanks a lot. Sorry, thanks a lot for the nice talk. So I was wondering if you have made studies on the generosity of this phi parameter with all the effects in the HOD, like halo suppression, or all the things that could impact also this one halo region.
Yes, I didn't go that much into details, but in my paper I'm measuring the effect on, for example, the concentration parameter. How is it varying if you're using the different concentrations in the dark matter in the halo? Yes, you know, this is a simple model. I didn't want to go, you know, too much into details because there are existing a lot of very sophisticated based on simulations. But yes, I did on the concentration. I didn't do on this.
Just to preface this, I don't know anything about it. Well, I know very little about HOD to be able to use it. When you were showing that your most massive halos, for example, are preferentially eggs, it makes me think like, okay, you're probably looking at parts of filaments, so yes. It makes it more. But does including this into like a definition of a halo create an issue further down the line of how you construct your statistical model?
Okay, so there is a number of assumptions behind this. So I was, of course, using the simulations for which there is an assumption that there is certain description of the halo shape, which in this case was an ellipsoid. So which, you know, probably is not. So if you're using more sophisticated simulations, you have, you know, dark matter particles where you can just define the shape. But this was created for small samples. of galaxies. Of course, it's not going to be super useful for, I don't know, Euclid, for example, right? Because you can go into these details with Euclid. You can't go for, like, for example, the high redshift samples where you have like 1,000 galaxies and you're measuring the correlation function. So on top of all of these problems, you have statistics, right? Yes, so there is this assumption behind that, that we are looking at the most bright galaxies in structures. So it might probably not work very well for voids and stuff like that. Thank you.
Hi, Marie.